I'm recording, so anything we say can and will be used against us, and you fill in the rest. All right, let's see. So far for this week, got a whole 1 day so far. By the way, welcome to Intermediate Algebra again, and for the exciting topic of algebra. Yesterday we did a lot of general administrative work. You met Nate. Hopefully Nate did good by y'all. Did good by y'all. Sorry he was doing Kahoot when I had to bail out because I had to get ready for another class. But we did do a general review of 1.2, 1.3, 1.4, of which we call this Saturday. This Saturday we will have the first set of assignments due. Basically, my math app homeworks for 1.2 through 1.4, 2.1, 2.3, and the video assignments that go with them. So there's still a few who haven't gotten on the My Math lab yet. So you really can't do this course without being in My Math lab. Okay. And getting into it is pretty easy. Basically, just pick anything that has that kind of looking thingy to it. Click on the button for that, navigate to it, and you either get a browser check or you get into My Math lab, or you're going to get a page that's going to ask you to accept some conditions, terms of use conditions, and you should be in. So it should take a whole, like I said, as part of your tuition purchasing the class for registration. So it should be seamless to get into. And start working the problems. I've looked and I see some people have already started them. Great. What they're going to do for each class is you can either unmute yourself or type in the chat, into the chat section, if there were any problems you worked on. I haven't done 2.1 through 2.3 yet, but anything that's been done previously up to the day before, a couple days before. In the homework set, if there's anything that came up, hey Bob, I was doing homework set 1.3, problem 7, and I was having problems with it. So if any of those are out there, like I said, I'll give you a few minutes to either chime in, unmute yourself and let me know what it is, or type in the chat box, oh, hey, section 1.2, problem 7. So I need to know what problem set, i.e. section, and which problem number it is. Let's have coffee. Now to all the questions all the questions I got wrong, and you found out the issues later. Okay, that's cool. Now, that's good to hear. I guess you used some of the help features that came with it, or with the book. But hopefully you also went back and reworked those questions to get all the credit, the points for it. Like I said, if you're doing a question and got it wrong, all you gotta do is hit to do a similar problem, and it'll pop up a new problem, kind of sort of like the one that previous ones, and allows you to go and do it again and get the full points for it. So hopefully you've done that. I will know that when I go go in my grade book and look at it. So thanks, Joe. Joseph. Hey, chat. Okay. And then the courtesy there. Okay, I'm going to say take that as being currently no issues, which is fine. Mind you, the due by midnight Saturday, as shown on the left right-hand side of the calendar there, including the video problems. Also, to do recall if there is it's due date, but if you get them late, if you get them on Sunday, there's 50% deduction for any problems that were worked after midnight. Do them on Monday, 30%, and so forth. Aha, I got one. Section 1.2, question 4. Okay, let's go take a look at that one. Let's go take a look at that one. Now, I'll be doing it. It may not be the exact same problem you have, but it'll be the same type because I forgot to mention this is an algorithm, and it makes for similar problems, but not same type, but different. Okay, well, here we go. What do I want? Let's see if I can get right into it. Point 2, number 4. Here's the videos you got to do, and at your convenience. I did it before class, just kind of like watch them. Number 4. Okay, so problem should look that ilk. Okay. Same idea, and it may be something, maybe instead of 4, maybe 5 or something like that. Okay, so the good old word problems. Yeah, I love word problems. Seriously, I do love word problems. Okay, so it's kind of like trying to decipher the verbiage. All right. Now let's see what we got here. And something else you're going to find, I never have a short answer for anything. Okay. Twice the sum. Okay. 2 operations. Okay. Twice is kind of like implies 2 times something. Quadruple, triple, quintuple. Okay, so it's giving me 2 operations. Let's put twice, right? Yeah, 2 operations. I do an operation, then do an operation. So twice the sum. So 2 times something. Okay, 2 times a sum. Okay. Well, to have a sum, I got to have 2 things to talk about. The 2 things we're talking about is a number, which I don't know what it is, and if I was on video, I'd say that's one of those head scratches. A number, what number? I don't know. I don't know. So if you don't know what it is, it must be a variable. So twice the sum of a number and 4, or 2 times. You should accept either one, but either one. So let's see. Does this fit? I'm looking for twice the sum of a number and 4. Let's see how that works. I'm curious. 2 times parentheses. Let's see if this works. I really don't know if this is going to work or not. It accepts that. I know we'll accept this one. We'll accept this one. Yeah, I did. All right, interesting. All right. That's the problem. Okay, this one. Twice the difference of a number and 8. I'm recording, right? Yeah, like that. Again, we have twice the difference. Again, an operation, a multiplication, 2 times, and a difference, subtraction. And this is kind of like what I sometimes call the hiccup. No, it's a boom boom. No, operation, twice the difference. Well, then you gotta look at twice the difference of what? The difference between a number and 8. I'm just curiosity, I'm gonna try different variable. Let's see, here we have twice the difference between a number and 8. Curiosity, try this guy. So we do 8 minus z, twice between 8 and a number. What's the hint? There are 2 key words, twice and difference. Use these words to determine the operation that will be involved in translating a given phrase. Pay special attention to their groupings. Z minus 8. See, that works. Just seeing how sensitive this guy is. Ah. Okay. I guess. Duh. Duh. Tells you use X. Okay. Now, didn't I say you got to read these problems carefully? Usually what gets you the stuff they have in blue in parentheses, usually I have to answer. So Bryce, that help? Cool. Okay, I lost. There we go. All right. How do you get out of this thing? Okay. Any other ones? Good question, by the way. That's usually one that just people may have trouble on. Any other questions? Something I added. Good. All right. Is I've put in the Blackboard just before in chapter 1 something called word problem Rosetta sheet. Hint, good sheet to print out for notes. And I'm going to zoom down a little bit. And it's a bunch of buzzwords. And it's pretty good for word type problems. Words that mean addition, words that mean subtraction, division is multiplication. And if you go on the bottom, parentheses words, which is exactly what we had. It was parentheses word. Times the difference, twice the sum, plus the difference. Notice in each case, it's boom, boom. Operation, no numbers, no variables, times the difference. No, 2 times the 3 times the difference. So I'm going to multiply. So like for these two here, I'm going to have, it's going to be multiplication. And of course, it's from this guy and this guy that will have there's something on the outside. Plus the difference of, that'd be something like a 5 plus, 5 plus the difference of a number and 2. Something like that. So feel free to print this guy out, okay, and have as part of your notes. Another one that is a good one are what we call these turnaround words, which really only affect subtraction. So 5 less than x. So less than is one of those turnaround words. What that means is we'll change the order of presentation. So instead of 5 less than implies subtraction because we're going less. And the only way I get less is to subtract. But the turnaround means it's not 5 minus x, it's x minus 5. Or 5 fewer than x. And I'm going to take x and make it 5 less. So the other, besides these, what I call my hiccup words, are these turnaround words that sometimes can cause problems. Beware of that. Whoa, off my eraser. Oh, definitely hurts bending down like that. So, by all means, learning plan 1, before the 2 chapters, lesson problem Rosetta sheets. Feel free to print it out or to download it onto a thumb drive or on your hard drive or something like that. All right. I'm going to take it as we're good to go for on 1, 2, 1, 4 then. So let's look at chapter 2. Specifically 2, 1 through 2, 3. So linear equations, one variable, introduction to problem solving, formulas, and problem solving. So what do you have in this section for homework or, okay, reading and study. We got our videos, PowerPoint to look over if you so choose. And you don't see the orange. You won't be seeing the orange. This is from a different older section. And then of course the 2.1 homework. Okay. Uh, 2.2 similarly, read and study, video and text. That's the assignment. So this has points attached to it. PowerPoint, so choose, and of course the homework. You don't see the orange. There was 2.3. Can read and study section. The video and text, which is homework. PowerPoint is so choose, and of course the iMathLab homework for the section. So let's talk about these things. Uh, 2.1 linear equation in one variable. A linear equation. First thing, and one variable means I'm only going to have an x, a y, one of them, not more than one. So one variable. So there's only one unknown. And being linear, it means I'll just be having powers of 1. Not power of 2, which is quadratic. Not power of 3, which is cubic. Not power of 4, which is quadric. Okay. So when the classical linear equation will be, hey, oh, that's 2 variables. It'll be something like g, x minus 5 equals 7. Now, if I only have one equation, one variable, I can solve that. If we have 2 variables, I need at least 2 equations. Two independent equations. 3 variables, we need 3 equations. So if I have an x minus 5, or y minus 5 equals 7, or z minus 5 equals 7, I can work these guys to find what x is going to equal, what y will equal, what z will equal. And right now, in doing variables, the idea of any problem, no matter how complicated it is, topside, you want to work it down to just a variable equals a value. And how are we going to do that? Well, believe it or not, word of operations. In a way. Yeah, I'm a little ahead of myself here. But when we're doing linear equations, means I'll have stuff to the left, stuff 1 equals stuff 2. Yeah, stuff is a technical term. It means yada yada, okay, in math term. Okay. So the goal is, with a one variable term, a linear term, is to get my stuff on the left, my stuff 1, to be basically a variable made with a coefficient plus a constant. And I'm going to do stuff 1, get it to stuff 1 ax plus b by going down order of operation. So I'm going to look at the left hand. I'm going to look at, do I have parentheses? Do I have exponents? Am I multiplying, dividing? Am I adding, subtracting? Work that. And if you have a linear equation, one variable linear equation, you will get down basically an ax plus b, maybe an ay plus b, I don't know, or az. Then you do the same thing over here. Maybe start with parentheses, exponent, math, multiplication, division, adding, subtracting. Get it down to where I just have a variable term and a constant. All right. Okay, now we have this one. And I'm going to show you in a second, we're going to have to start moving things back and forth, left and right. And when we're moving across the equal sign, we're moving things over between the left and the right through the equal. We want to use order of operations, but again, now we're going to go up from the bottom. So the first thing we're going to look for in our expression is pluses and minuses. And let's just say, okay, plus and minuses. And let's see. We have pluses. So we're going to do any kind of adding, subtracting operations first. Basically move the constant or the variables. Get the variables to one side, the constant to the other side by adding, subtracting. Uh-oh. So after done with adding, subtracting, you may have, I'm just going to, after all is said and done, you add, subtract constants, so forth, and you end up with 3x plus 6. Okay. Just for sake of argument. Well, now what do I have on my variable? Well, I have a coefficient, and it's with multiplication. So we've done addition, subtraction. And the last step is either some kind of multiplication division operation. Okay. So that's basically going to be, we're going to start basic and build up more complex. And as we get more and more complex in the expressions, the left term and the right term. Left term and the right term. We're going to use order of operations to help us. So let's get to where we were. X minus 5 equals 7. And again, the goal is x equals something. So when you see it, when you linear expression, you ask yourself, look, the left and right. On the left, is the left, is that as simplified as I can get it? Is there any x's I can combine? Is there any distribution that I can do? Is there any exponents I can take care of? The answer is no, 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 no. In fact, this is already. I'm doing that. Why is this not moving? I hate when that does it. This guy is already in ax plus b format. It's in the condition I want. And same with the right. It's just 7. It's a constant. So now I'm ready to move things. So I think it's obvious I'm not going to. I already have the x on one side. I just got to get that 5 moved. Just gonna move that 5. And I have a minus there, minus 5. So the goal is to add or subtract 5 in some way that when I'm done, I have 0. So if I add 5 over to here, they cancel. Now the other rule is what you do to one side, thou shalt do to the other side. So if I add a 5 to the left, I have to add 5 to the right. Basically means x equals 7 plus 5, 12. Yeah, I know I took a lot more time than probably needed, but like I said, I don't give short answers. Better or for worse, that's my mantra. All right. We have some. Something like x over 4 equals 3. Believe it or not, that's already good to go. Because I really rewrite this as 1/4 x equals 3. So I have an x term on one side and other constant on the other side. I have nothing to add or subtract. I am multiplying by 1/4. So when it comes to fractions, it's easier just to multiply it by the reciprocal. The multiplication, the goal, with the last part, with the coefficient, the goal is to turn that coefficient into a 1. And we'll either do that by dividing by the coefficient if it's a whole number, or multiply by the reciprocal if it's a fraction. Again, do the left, you got to do the right. And of course, what's 12 divided by 4? 3. Those are some basic warmer-uppers. Let's go to some more serious ones. Let's try 3 times 2x plus 4 equals 9x minus 3. Now I'm looking at the left-hand side. I got parentheses. I got some distributive property that I can do. It's not looking like the right side. Coefficient, variable, plus or minus some constant. So I have parentheses, so we need to take care of that. So let's do that. 3 times 2x, 6x, plus 3 times 4, 12. Let's clear that one. Is there any exponents? No. Is there any multiplication division that I can do? No, taken care of. Any addition subtraction on the left side, the x term will not mix with the 12. On the right, the x term won't mix with the 3, the constant, so we're good to go. So now I'm ready to move things left and right. So I have both addition and subtraction on both sides, so I do know I have to do an adding, subtracting. At this point here, the question is, where do you want the x's to go? Do you want x's on the left or x's on the right? Now, generally, consensus universally is, let's do the x such that we always end up with a positive x. Whenever given that option, people always say, always subtract the 6x, because I want a plus x when I'm done. Makes for easier math at the end, and it does in a way. So let's move. So let's move the x's, because it's a plus here. To unglue the 6x from the 12, I'll subtract 6x from it. 6x minus 6x is 0. And same over here. The first stage, when I'm physically moving a term, I want it to go to 0. So now I have a 12 equals 3x minus 3. All right, so I'm going to have my x on the right now. I still have an addition subtraction term, which means I'll move that 3 by an addition or a subtraction. Whatever combination makes that a 0. If I add 3 to both sides, that goes to 0. And now I have a 12 plus 3 is 15. That's 3, right? What the heck? $15 equals 3x. Okay. On both the left and the right, there are no more addition or subtraction signs. No addition or subtractions means now I'm looking at multiplication or division. I have 3 times x. I want x. So I need to make that 3 a 1. This is multiplication. I'll divide by 3. Same thing over here. So it looks like x equals 5. Let's do a quick check here. I'm looking up here now. 2 times 5 is 10. 10 plus 4 is 14. 14 times 3 is 42. 9 times 5 is 45. 45 minus 3 is 42. Checks. So the key to doing these guys is really order of operation. Order of operation on the left, going from parentheses down to adding subtracting. Order of operations on the right, parentheses down to adding subtracting. Get all stuff down to ax plus b equals something similar, bx plus e. And then doing either, we'll go back up this way from the bottom, adding, subtracting, multiplying, dividing at the end. It's all good stuff. Close. Oh, didn't expect that. Let's kick it up a notch. How about minus 2, 3n minus 1 minus n equals minus 5n minus 4. Single equation. I only got one equation up there. Single term. All I see are n's, not m and n's, not x's and y's, and not z's, just n. But I see a lot of parentheses and a lot of minuses and pluses. Oh, no pluses. Parentheses. So let's look at one side at a time. One expression. Left expression equals the right expression. And again, let's go down the order of operations. Start with parentheses. Inside the parentheses, 3n minus 1. Is there anything I can do inside to make it less complex? Can I combine that 3n with the 1? The answer is no, I can't. What I can do is distribute minus 2 the inside. Of course, we do that. Minus 2 times 3n, well, 2 times 3 is 6, so minus 6n. Minus 2 times minus 1, or negative 2 times minus 1. 2 minuses make a plus. So plus 2, so there's minus n here. All right? Not done with the side yet. All right, so now I have an n term plus a constant and another n term. Okay. Now, my n's I can combine. N's will play with other n's. X's play with x's. Y plays with y's. Constants play with constants. So I'm 6 feet. I dug down 6 feet in the hole. I dig down another foot. So I'd be how many feet down? Well, both are going in the same direction. Both are going negative. So minus 6 minus 1. Well, minus 7n plus 2 then. And now the n and the constants, that's as far as we can go. Same thing here, inside the parentheses, the n minus 4. Anything I can do? No, but I can distribute. So minus 5 times n, minus 5 times minus 4. And I do those little arcs. I do these guys for a reason. Is to remind me that that 5 has to hit both terms. I mean, you would be surprised, maybe not, how many times I'll give a problem like this, and I'll get for an answer. The joke being, no one misses the first one. Everyone gets multiplying the first term with the outside, but a lot of times, for some reason, people forget the second one. So I just use this as a little reminder that I have to also multiply both the terms inside by that number on the outside. So it's a little crutch I used, and it's effective. All right. So basically now we're down to expression. As far as I can get by expression, as far as I can get on the other side. Now we gotta go up. So now I want to move things. And negative is too hard. I'm just going to do this. I just want the end on the left. In the end, it'll all be fixed. You get an idea being, again, there's both sides has an addition in the expression, which means I move things or I break the glue between the items that's attached by the plus by either subtraction or addition. So minus 7 plus 5 is a minus 2n. I start having addition here. So that's the glue. To unglue from the 2n, I have to subtract 2. Of course, that's equal. Eliminates those guys, and I have an 18. And last but not least, not 2, but minus 2, because when I'm done, I want a positive 1 in front of the n. Of course, minus 2. So it looks like n equals a minus 9 in this case. Okay. So we've been inching up from simplest to more and more complex. But I've been following some very, very basic guidelines, order of operations. Can't go wrong with it. Okay, let's crank it. Let's go up another crank it up another notch. How about 2x over 5 minus x over 3 equals 5. Oh my gosh, we have fractions. On top of that, we have two fractions that don't have a common denominator. How am I going to do this? Oh my goodness. Well, we know the golden rule of adding fractions. Got to have a common denominator. So I'm going to do this two ways. We can either, I have x's and x's, and I'll put them together. But I need to get a common denominator. Between 5 and 3, now 5 is 5 times 1, 3 is 3 times 1, so both prime, 15 is the answer. So we could go this way. 5 times 3 is 15, 5 times x, 3 times 5 is 15, 3 times 2x. We could do it this way, which then gives us 6x over 15 minus 5x over 15 equals 5. Because of a common denominator, I just got to worry about the numerator. So 6x minus 5x is just an x. Right? Multiply by reciprocal. Cancel, cancel. So x is 75. Wow. Right. That's one way of doing it. Another way I kind of call sweeping the denominators. Sweeping the denominator. Let's totally get rid of the denominators. And so what I can do is right away multiply every term, including the other side of the equal sign, by a number that when I'm done, the 5 goes away and the 3 goes away. Oh, I had a check here. Let's see. In fact, I need to multiply like the 5, 2. Oh, never mind, I see. Oh, okay, yeah. Gotcha. All right. I just use one parentheses. So if we multiply everything by the number that essentially becomes a common denominator, would have been the common denominator, I can basically just eliminate the denominator numbers. So what number does 5 and 3 both share that if I multiply through gets rid of them? And that number is 15. So that guy by 15, that guy by 15, and that guy by 15. So I do that. Well, let's see. If I multiply, and let's do it all by hand. So it'll be 15, 2x over 5 minus 15x over 3 equals 15 times 5. Little cancellation. 3. Little cancellation. 5. So when I combine the 3 with the 2, I get 6x minus 5x equals 75. Of course, this is x equals 75. So either way works. I'm not going to give you tell you how to do it, but people have preferences. People gravitate towards a specific way of doing something. And these are two options. I can either work with a common denominator. We can either work with like I said, on the left side, over here with a common denominator, and at the end, multiply through by the denominator, or essentially over here, multiply by the common denominator first, and get rid of the denominators. Like I said, it's a personal preference. And pretty much every other question is kind of like a variation of these guys. These things. That's basically 2.1. Okay. 2.1? Yeah, 2.1. And curiosity, what they say about curiosity, you never good. I covered up what's needed for these things. Okay, yeah, you should really do that one. That shouldn't be a problem. That's which means okay, 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 okay. Same idea, give it a denominator, multiply through everything by 8. Multiply through by 10. Find the error, that's on you. Uh-oh. And what's our numbers? And this may have to do some of the readings. Pretty much looking good. Yeah, I think we'll discuss that a little bit. Yeah, I think I should. There's basically 3 solutions you can get. Solution is, hey, x is a number. Yay! X is 5. Woohoo! All right. You may end up with the x's cancel. All the x's go away. X equals 3, 0 equals 3. Let's be like x plus 2, oops. That x equals x plus 3. Hey, subtract the x's. Hey, that is the algebraic solution. But something like that, the question is, does that make sense? Is that a true statement? Could, in this universe, does 0 ever equal 3? Does 3 equal 0? And the answer to that question is no. This is what they call an inconsistent answer. And that basically means no solution. Another possible outcome is, I don't know, I'm just gonna make this one up. 3 equals 3. In algebra, the x's, the variables cancel each other out. They went away, and you end up with a constant on both sides. The question that asks up here is this a true statement? Is this true? So it means it's consistent. Don't judge my spelling here. Constant. Consistent. This means all real x, or all real y, or all real z. Basically, any number is good. Because this will look like something like x plus 3 equals x plus 3. No matter what value I put in, if I put in x equals 2 here, I also had to put in x equals 2 here. Of course, 2 plus 3 is 5. And that equals 2 plus 3, which is 5. I put in x equals 7. Again, I got to put 7 on both sides. 7 plus 3 is 10. 7 plus 3 is 10. Yeah, so there's always 3 possible solutions in nearly everything. Either a single solution, no solutions, or a lot of solutions. Okay, I think I covered that one real well. Hey, 2.2 problem solving. Again, this is basic word problems. 2.2 is word problems again, except it's going to be a word problem that has something equals something. So let's try a couple of these here. I always like this guy. Let's find the sum of three consecutive integers if the first integer is x. Okay. How would you describe the sum of three consecutive integers if the first integer is x? Okay, so that'd be like let's see, what's three consecutive integers? 100, 101, 102. I just made a quick model of three consecutive integers. Now it says let the first one be x. Well, to get to 101, so I can also write it as 100 plus 100 plus 1 plus 100 plus 2, right? 100, 100, 101, 102 are three consecutive integers. I can write 100 as my first term, 100 plus 1. 102 as my first term, 100 plus 2. So then if I let 100 be x, that would make 101 equivalent to, well, if 100 is x, x plus 1. And 100 is x, x plus 2. So one strategy is do something you know, do something you can actually visualize, and then kind of create your model out of that. And of course, what do I have? I have what do I have? I have three x's plus 1 plus 2 plus 3. And so sometimes, try and, like I said, create a model. And again, for this 2.2, I would have, as an aid, I'd have that sheet of Rosetta Stone for word problems out and printed next to you. Okay. Oh, here's an interesting one. One number what number? I don't know. Is 2 times another number. Another number. Period. The sum of the numbers is 90. Some of the numbers are 90. What are the two numbers? All right. Now this one is a little different than the other ones. I mean, it's gone for one variable, and we actually have two variables here. So it's actually, we actually have two variables because it says one number. I don't know. So let's go to the first part. Let's figure out what this guy is saying. One number is 2 times another. One number. What number? I don't know. Is. Whoa. Is. If you go to the, come on, get out of my way here. If you go to this page, the verbiage in a word problem of is means equal. So one number is 2 times another number. Well, it's not the same number, it's a different number. But what number? I don't know. Let's call that guy y. So whatever y is, x is twice as big. Next question. The sum of the numbers are 90. So whatever x is and whatever y is, you gotta have 90. You gotta have 90. Okay. So here's our first foray into two variables. Two variables, two equations. I have two variables, x and y. Do you have two equations? Yes, I do. X equals 2y, and x plus y equals 90. They're totally different. They're not the same. The key to what we're going to do now is the fact that whatever the value for x is in this equation, be it a 1, be it 2, be it 3, has to be the same as this one. So the value 20 satisfies the first equation. X equals 20 has to satisfy the second equation too. So what I'm allowed to do here is, hey, I'll combine these two guys. This x and this x is the same, which means that x equals 2y. So if I combine these two guys, remember, x plus y equals 90. And since x equals 2y, that means 2y plus y has to also equal 90. That's called substitution. What I effectively did was just turn an equation with two unknowns into an equation with one unknown. And with one unknown, I can solve it. I'll just add these two guys up. And then divide both sides by 3. I find one of my values is 30. Now, since y is 30 and x is 2 times 30, recall, x equals 2y, that means x would be 60. 30 times 2 is 60. Oh, and 30 plus 60 equals 90. Oh yeah, something to 90. R. Is R in there? Good question. Where am I at? Here we go. I kind of like rushed myself here. But some of the numbers are 90. Okay. So where's the equal sign here? I did by what's reflex. Look over here on the terms. R. Something something R something. R. That's equal. That was a clue. That right there was my equal sign. The sum of the numbers. What numbers? I have two numbers, x and y. Sum, it says add them up, x plus y, r equal 90. That's not a good one. Here's a good one. Today, Henry is 7 years older than twice his age of 23 years ago. Find Henry's age. So I think it's put Henry wrong. Ease. I'm sure some Henry spells it like that. So today, Henry is 7 years older than twice his age of 23 years ago. Find Henry's age. I want you guys think about this for a second. In case they're muddling over, I'm going to put a little clue in here. This one's a little convoluted. But there are a lot of clues in here. Biggest thing is find what is the variable x. What would x equal? Think about it. X is Henry's age. So just reading this through the sentence, it looks like x equals 7 years older, okay, a value and an applied operation. Okay. So to get older, would that be would I add, subtract, multiply, or divide from the downstream items? Well, to get older, okay, he's going to be 7 years older. 7 years older than what? Well, then twice his age, okay, of 23 years ago. Or twice the difference of his age in 23. So twice his age 23 years ago. Well, what was his age 23 years ago? Or Henry's age today minus 23. Let's see. Henry's age is 7 years older or 7 years more than twice what his age was 23 years ago. That's something else I always do when after I write what I think the equation is, I read through the problem again and see if I can click off all the pieces parts in an order that makes sense. Again, Henry's age is 7 years older than, or 7 more than, twice something. Twice what? His age of 23 years ago. And how do you get his age from 23 years ago? Is to age today minus 23. Now we gotta finish this guy up. X equals 7 plus 2x minus 46. So let's see, x equals a 7 minus 46 would be a minus 39 plus 2x minus 2x. So minus x equals minus 39. So I guess his age today is he's 39 years old. So let's see. If I subtract 23 from 39, that is 16. That's 16. 16 double is 32, and 32 plus 7 is 39. So he's 39 years old. I remember when I was 39. That was a long time ago. Okay, do one more, and we're gonna we're going for one. We'll take a break. Let's see. Here we go. A 7-foot board is cut into 2 pieces. So that one piece is 3 feet longer than 3 times the shorter piece. If the shorter piece, this is nice. If the shorter piece is X feet long, find the length. Find X. Find the length of both pieces. Find length of both pieces. All right. So let's see. What do we have here? If I visualize it, seven feet long. Cut in two, and this guy is X, and tells me that the other piece is 3 feet longer than 3 times the shorter piece. Well, that's a shorter piece, so 3 feet longer than 3 times the shorter piece. Does that look about right? 7 feet, cut in two. I mean, one side's shorter than the other. The problem tells me specifically to name the short piece X. And the other one says it is 3 feet longer, so plus 3. 3 plus what? 3 plus 3 times the shorter piece. And the shorter piece is X, so it's 3 times X. Yep, that looks about right. And looks like the equation is going to be X plus okay, how did that happen? Short piece plus the long piece equals 7. The long piece is 3 plus 3x. And I combine it gives me a x plus 3x 7. And that's an addition, so I'll move the plus guy. So 4x equals 4 divided by 4. Declare the coefficient. Those can't be 1. Those my short piece is 1. And my other piece, I'm going to call it y. Y would be 6. 1 plus 6 is 7. And 3 plus 3 times 1 is also 6. And so don't be afraid, or don't feel that you have to always do things math up algebraically. Graphics are great. Sketching out the problem sometimes helps a lot. Does me at least. Okay. Been going for a while. So why don't we take a 10-minute break? All right. Recording again, which is good. Screen. All right. So word problems. What does 2.2 look like out of curiosity? And problems. Okay, for kind of cover that deal. It kind of defines the areas. Just got them all up. And this problem, don't forget, as part of the addition is also these. So you got this guy, this guy, this guy, this guy, this guy, this guy, and that guy. So for the total amount of fencing needed as an expression. So don't forget these two fences. Trimmers. Okay. Oh. Okay. We know it's 5 feet. So okay, I'm up. Should be a problem. And one of those problems I need to do. Okay. We do. Okay. And one more, then we'll do finish up with formulas. Okay. Let's see. Major car manufacturer, major car company announced it's going to lay off 17,000 employee layoffs. Okay, saying this is 20% of its workforce. Find the size of the workforce prior to the layoff. Workforce prior to layoff. It's written that right. Okay. So basically we have two numbers here. We have 17,000 and 20%. And so a quick thing on proportions, on percentages. So let's see, as a percentage, let's see, basically it's like the part over the whole equals percent over 100. Okay. There's also another way of looking at this is the is over the of equals percent over 100. What is a buzz, yeah, it means equal, but also in terms of percentages, kind of like equates to what the part is. And the whole usually goes with the of. And that goes with the 100%, the whole is starting point. So we have a number. We have 17,000 and 20%, and we're trying to find a third number. Well, the 20% is easy. Where that goes. That'll go over here. Okay. Question is, the 17,000, is that the part or is that the whole? The part usually is from the whole. The part usually typically is smarter than the whole, not always, typically. So 17,000 employees layoffs. This 17,000 is 20% of its workforce. Okay. So, okay, 20% of what? 17. Okay. of its workforce. So 20% is going to separate the is from the of. So it looks like the of is what we're looking for, and the 17,000 is the percentage of the total, the whole. Okay. A lot of times when you do these self-talks and try and distinguish the pieces parts of the problem, and let's see what that gives us. So it would appear that 17,000, I'm going to say x, and 20 over 100 is 0.20. It was return the decimal and set into a decimal equivalent. And let's see. And multiply both sides by x. That gets x out of the denominator. And now since I'm multiplying, if I divide by 0.20, that tells me that's what, times 5, 85,000, I guess. Divided by 0.2 is like multiplying by 5. No problem. 85,000 employees. All right. Is that what that problem looks like? What's different, but it gives you an idea to start with, though. And any question you have problems with, you can always ask for it and ask about it in class test. All right. Uh-oh, too far. Too far. Chapter 2, 2.3. Formulas and problem solving. And I'll finish up what we need to do for today. Okay, actually, it's kind of like a continuation of 2.2. Only thing difference is a formula is just an equation that's equation specialized. So it's an equation, we have formula. Hey, no. We don't say what's the equation to the circumference of a circle. No, we say what's the formula to the circumference of a circle. Now C equals 2 pi r, circumference 2 pi r. What's the area of a circle? We say the formula. The area of a circle is pi r squared. We don't say what's the equation for the area of a triangle. We say what's the formula for the area of a triangle. The formula for area of a triangle is 1/2 base times height, and so forth. So formula is just an equation. Equation that, you say specialized, has a job, has a function, has a specific variables. R is radius, C is circumference, B is base, H is height. What What's the formula for perimeter of a rectangle? The perimeter is 2 lengths plus 2 widths. 2L plus 2W. Okay. So that's our formula. That's our formula is. It's an equation. Equation to a straight line. 4x plus 2y. Yeah. Equation, a linear equation, equation to a line. Mx plus y equals mx plus b in the standard form. That's all formula is. It's just an equation. And with an equation, or excuse me, with a formula, in a lot of cases, though, depending on what you have, let's go with the circumference here. Okay, c equals 2 pi r. That's the equation for given the radius, find the circumference. So this one assumes r is known. But hey, what happens if, well, I should say r is known, find c. But what about I know c, and I want to find r. I have a lot of formulas memorized, but I usually memorize the easiest form of the formula. Because if I have the problem in red, I know my circumference, I want to find r. Well, I'm not going to memorize the r equation, sorry, the formula for r. I'm going to know c. Okay? I'm going to start with this guy, and I'm going to want to work it to where it's just r, which means I got to get the 2 and the pi moved. Obviously, 2 times pi times r is multiplication. No, I divide by that. So now I rewrote the circumference formula from which r is the known, c is the unknown. I rearranged the two. Now I know c. I'll use it to find r by dividing c by 2 pi. So the formula is just an equation. And all the equation balancing rules apply. Let's look at this guy. Okay. This is the formula to convert Fahrenheit to Celsius. So again, F is known. Find C. However, what about if C is known? Find degrees Fahrenheit. This is the easy. I guess some people think this is the easier formula to remember. But okay, hey, we'll start with Celsius. Can't do that. Okay. And I want to get it down to F. Now, what I see is the first thing I need to do is, yeah, I can multiply through by 5/9, but I also have to just undo it again. So why don't we just multiply both sides by 9/5. Cancel, 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 cancel. So that tells me 9/5 C equals F minus 32. And the last thing to get F by itself is to have this guy cancel out. So it looks like 9/5 C plus 32 degrees gets us the degrees Fahrenheit. And sometimes it's good to break the rules a little bit. But again, it's just using the order of operations. But sometimes you have to know when to break the rule. Or deviate from the rule. I'm not breaking anything, just deviating. I'm not sure what the problem sets are for this one, but compound interest is a formula that's used a lot. Yeah. Compound interest? With compounding interest versus simple interest, first of all, simple interest is an easy equation. Basically, your interest is PRT, principal, rate, time. Compound interest is your amount, your principal, 1 plus R over N, NT. So it's a little more involved of the equation. The good thing about it, all we're going to do is just always look for the amount. Okay. Pieces parts, principal, which is the amount of money you started with. N is number of compounding per year, from number of compound periods. T, time, obviously. And of course, R is your rate, interest rate. All right. I'll be careful here. Gotta make sure everything matches. For interest, for instance, say R is 8% annual. Okay. Annual means on a yearly basis. Let's just say you're compounding quarterly. That tells you you're going to do it 4 times a year. Semi-annual is twice a year. Annual is once a year. Monthly is 12 times a year. All right. And T, okay, so 4 times a year, annual. And T, okay, well, the rate is annual. The compounding is in years. So time should also be years. 1 year, a half a year, 2 years, 3 years. what mistakes happen is, okay, rates annual, compounding period is how many times a year, and they give you 12 months. Okay. Well, 12 months is not months is not years, so be careful with that to make sure all the units match up. That's usually where they get you. Okay, so there's the background. So the problem is Emmanuel. Let me just on one board. And Emmanuel puts 5,010 dollars at 9% compound semi-annual for 12 years. How much would he have? How much would it have grown to? Okay, well, from the problem, I know P is 5,010. R is 9%, which is 0.09 is a decimal. Another thing people forget, they forget to change to a decimal. N is 2, because twice a year you're going to compound, you're going to calculate your interest. So N is 2, and T equals 12 years. So 9% a year compounded twice a year for 12 years. So year. So all my time units line up. So 9% twice a year, doing it twice a year for 12 years, which means in 12 years, twice a year, I have 24 compounding periods. 24 times I'll compound it. Which is what this tells me. So let's see, my amount should be 5,010. 1 plus 0.09 over 2. So 9% as a decimal, 0.09, twice a year, so 4.5% every 6 months. And twice a year times 12, 2 compoundings per year times 12 years is going to be 24 compoundings. And now it's just now it's just calculator work. So calculate work. Let's do that. So let's do 5,010 times, these parentheses, 1 plus 0.09 divided by 2. Okay. And I'll raise that to 2 times 12. The principal, 1 plus R over N times T equals. So it grew to $14,408.83. Am I correct? Yes, I am. Okay. So this one, anything compound interest, you got to recognize the equation to use. Compound interest is more involved than simple interest, or compounding amounts is Simple interest. So now, let's say the question was, okay, what was the interest that you earned? How much interest did you earn on the $5,010? Well, the interest now for compound interest is basically going to be the amount minus the principal. Because $5,010 is what you started with. You start with 5,010. Anything that was added onto it to get you to 14,408, that's the interest. There's another thing they sometimes do is and actually this one caught me on a test for a certification test once because it doesn't read the full problem. Minus 5010 93 98 83. Okay, so in 12 years, you almost made twice as much in your initial investment in interest, and you almost tripled your money, just shy of tripling it. The power of compound interest. Another interesting problem you may see in here. Is that rain? Yeah, rain and wind. Okay. Another word problem. Problem-solving problem. Your office space problem. Okay, you're renting an office space. Renting an office space. And it's costing you, let's see, $2,040 per month. Now the office measures 17 feet by 20 feet. Now how much are you paying in rent per foot? Per square foot? Per square foot or feet squared. Well, in some ways, it kind of tells you what you're looking for. Basically, from here, I'm looking for dollars per feet squared. Well, and then where do I have dollars? That's the cost per month. Where do I have measurements? Well, I have the length times width. Oh, wait. It's a rectangular measure. Of course, the area is length times width. And the length is 20, the width is 17. Or 340 feet squared. So in many ways, the units tells you whether you're going to multiply, divide, add, subtract, whatever. So in this one, the fact that I'm looking for cost, dollars per square feet, basically tells me it's going to be the cost over area. course, the cost here is 2,040. Area is 340 feet squared. And that's too much math for me to do. 2040 by 340. Which is $6 per or $6 per square feet. I did not see that. I did not see that one coming. I did not see that one coming. Being a perfect number. So a lot of times in these problems, the units, what they're asked for, watch the units. A lot of times the units will tell you what the setup. And one last one we'll call it quits. A triangular piece of wood needs to be varnished. Okay, I got a triangular piece of wood. So triangle, right? All right. So right away, I'm thinking, so varnishing means to fill in between the lines. So right away, I'm thinking area. I'm going to have to need some area. Okay. Now the base of the triangle is 3 meters. The height of the triangle is 13 meters. Okay. Let's see. 1 can of varnish can cover 10 square meters. How many cans do you have to buy? How many cans? How many cans would be needed? Okay. So like I said, first I need area. Of course, that's 1/2 base times height. And I have that. 1/2 3 meters by 13 meters, which is 19.5. 0.5 times 3 times 13. 19.5. 19.5 meters squared. All right. All right. How many cans? All right. So let's see. I know I got just trying to figure out how the best way to explain it. All right. Let's do it this way. Yeah, here's 19.5. So 1 can gives me 10. So here's 10. So I have at least one can, which is 10 meters. So leaves 9.5 left. So I'm going to need at least another can. Okay. So it looks like it's going to take roughly 2 cans, visually, graphically. Okay. So let's see. So area is 19.5 meters squared. One can equals 10 square meters. So it looks like my coverage is 10 meters squared per can. So coverage unit coverage is 10 meters squared per can. Okay, I make this a lot hard. I make this way too complicated. I think once you get those, you know to divide the area by 10 meters per square. Should be 19.5 over 10. Which is 1.95. And then we can come up with a good argument for that one. And I think most people, once they realize what the area is, how many and what a can cover, you take that area divided by what a can covers, that tells you how many cans you got to have. Now here's the rub. The answer is not 1.95. That's how many cans you need. But you go into Home Depot or Menards or Ace Hardware and you're asking for to buy 1.95 cans of varnish, they're just going to laugh at you. And they're going to say, tell you what, I'll sell you 2. You can keep the leftovers. So the rub is, what was it? Question, how many cans would be needed? Since you really can't buy fractional cans, buy 2 cans. The thing is, for this one, you have to recognize geometry of being a triangle. Every triangle has a formula: 1/2 base times height. We've given both base and height, which got us an area of 19.5 square meters, which is actually quite a big. That's pretty big. Well, shoot, 3 meters is almost 10 feet. 13 meters is almost 40 feet. So 10 by that is a really big item. And a can and how much a can covers, divide the square footage, and you get how many cans. Okay, my voice is out, and it's kind of worn out. What these guys look like. Piece of cake. And bounce out, piece of cake. Solve for m, subtract, divide, piece of cake. Given the formula, just plug the 77 in and calculate C. That should be no problem. In fact, that's over easy. Got the area. Patch is covers 29 square feet and square footage. That's how many patches you got to buy. Of course, you got to always round the next whole number, even if it's 0.1. Okay, to give you volume, you got to find the height, so you got to arrange this to H equals. Oop. Now it's got to select the correct unit. Remember height, you know, that's a volume, that's a area, that's straight line. And formula, and that should be no problem. Wow. Whoever did these problem sets were being really, really, really nice to you guys. So you should be all set for doing the homework sets. So again, based by Saturday midnight, should have these guys completed, those three completed, and those three completed. So 6 sets of videos to go through, video sets, and 1, 2, 3, and 6 homework sets, and how to answer them in my math lab. As per the, I have it there, as per the homework here. So for Monday, is there a sheet or a link in the Blackboard that we could access with all of these equations? I'm not quite sure what you're asking for. If you're implying everything that I wrote up on the board, I am saving it, and I haven't quite gotten off my duff to do yesterday's, but I will be saving these as a PDF, and they will be being posted. They will be being posted typically in here right here. Here's yesterday's, and I'll post another one probably this evening still. That's a smart board presentation, 22 October today. So you have access to everything I did on the board. You have a copy of. Is that what you're referring to? Let's see. Yep. Okay. We're good to go then. Oh, I lost my syllabus. And I'll find it again. Yeah. So for next week Monday, hey, we slowed down. We're only going to do 2 sections. Next week Monday, it would be nice if you have watched the videos for 2.4 and 2.5. So prior to class, it would really help to have watched the videos for 2.4 and 2.5. I'm not sure where those things are again. Oh yeah. Stop clicking, Bob. Again, the My Math videos for 2.4 and 2.5. It'd be really good to have those. Again, you get a preview. You may have some ideas on questions you may want to have specifically looked at also, or type of problems to look at versus me just going through a script that I have that I've created for this class for problem demonstrations. Also, Monday is the last hour is going to be a date time. So another reason I have only 2 sections is because I only have about an hour and 15 with you, and I can get 2 sections thoroughly covered in an hour and 15, plus questions on 2.1, 2.2, 2.3 maybe. Again, I'm done talking. I will have today's board notes, turn the PDF and post it, and give me half an hour, and it'll be up. And I will have a good weekend, and I'll see you all Monday. And again, homework due for the Saturday, and say again, between Sunday and Monday morning or Monday afternoon, please watch the videos for 2, 4, and 2, 5. Video sets for 2, 4, and 2, 5. I lost a page somewhere along the line here. Here we go. And I should see, again, if you haven't logged in MyMathLab, do it for Monday and Saturday because you can't do homework otherwise. Adieu. Stay safe. It's raining outside. It's getting cold. We got no warm weather here. And hope to see you all present here on Monday. I'm done. See ya. Good weekend. Again, how do I get out of this thing? Let's stop recording.